Okay. The last time I came, I wrote down H at a certain pressure called P1 and T minus HIG, which is the ideal gas at the same temperature T, was given by 0 to P1 at the same T of, I think was V minus dV dt at constant pressure. Check to see whether I got that right, but I think that was what I had. Yeah, yeah. And some of you have heard of what's called the compressibility factor. Let me introduce it. One way to show the deviation from the ideal state. See, when you have an ideal gas, you write PV equals RT. But you don't have an ideal gas all the time. So when you don't have an ideal gas, you can write in what's called a compressibility factor, and it's adjust for the non-ideality with the factor called Z. This Z is a function of the temperature and the pressure, okay, or any two variables, temperature and the density, or the density and the pressure, but it's a function of any two variables, okay? So it's not a constant. Z is not a constant, okay? For a single component fluid, it's a function of two intensive variables. Okay, so if I substitute this inside here, I'll get something, but I'm going to do something else with it. Not only that, but something else. From common experience, if you take a fluid at a, say take, I don't care, any fluid you want, any hydrocarbon, perhaps, say at room temperature, 27 degrees Celsius. Hey, Chase, you want to sit down? Okay, 27 degrees Celsius, room temperature. It's a little warmer today. Okay, you can compress it into a liquid. Okay, just without too much of pressure. The lower the temperature, the lower the pressure you need to compress it into a liquid. If you raise the temperature, you need to raise the pressure in order to make it into a liquid. But there comes upon a point where the temperature is high enough that no matter what pressure you use, you can never compress it into a liquid. That state is called the critical state. Okay? In other words, there comes upon a temperature and coexisting pressure where slightly below that temperature, you do have a pressure at which you can compress it. Slightly above it, no amount will ever. Okay? So that state is called the critical state. And corresponding to the critical state, you've got a critical volume, a critical temperature, and a critical pressure. Okay. If I substitute this inside here, I'll get PCVC equals ZCRTC. That's all that happens. That's just the way in which you talk about the compressibility factor at the critical state. We'll come back and look at some diagrams, and we'll tell ourselves what the critical state looks like. What happens at the critical state is that the specific heat goes to infinity. Okay? That's what happens. The specific heat just becomes unbounded. Now, anything above the critical region is called supercritical. And supercritical is not something that you see ordinarily in your processing, but chemical engineers do find it extremely important, particularly in the oil recovery business. In oil recovery, tertiary oil recovery, when you do what's called carbon dioxide sequestration by sending CO2 into the ground, the CO2 goes extremely deep into the ground, a few miles deep. The pressure is extremely high, and the CO2 is in what's called the supercritical state. Okay? So that's why we find these that state kind of interesting. But there's more to it. I can actually use that critical state to say something about this quantity, H minus HIG, and I'm about to do it. I'm going to do it by way of scaling. I'm going to do two things. I'm going to use PV equals ZRT here, and I'm going to use the critical state to say something that you will say, gee, now finally it looks like a diagram that you can use in the event that you don't have a computer to dial in these properties. Okay? Okay, so let's Basically, it's dealing with circular coordinates. You can see that here. Okay, so let's substitute this inside here. And what I have here is for V is equal to ZRT divided by P. And dV dt inside here is equal to ZR divided by P. Okay? Don't try and integrate this. Just put stuff in and see what you get. You got a question? Yeah. Okay, so we're going to plug this inside here, and we'll get the left-hand side is equal to H minus HIG is now equal to this integral, where I now go and write ZRT divided by P minus dV dt, which is ZR by P dP. Okay, not sure how much I can get out of this, but something, I suppose. Okay? Okay, so I think I got that right. This is V is equal to ZRT by P. dV dt is just, oh, I'm not done. I was careless. This is dV dt is ZR by P plus RT over P dZ dt. Good. Okay, so dV dt, the constant is this. So I now need more stuff. I need more stuff up here. So I've got for V ZRT over P, and I think there was a T here. I think people remember that. So I've got here ZRT over P minus RT squared over P dZ dt at constant pressure. Good. dP. Help me just send bar. Some nice things happen. This cancels. And we get, as a result of this, integral 0 to P1 of negative RT squared over P dZ dt at constant pressure dC. Now, by now, many of you, having taken fluid mechanics and heat transfer, are masters of dimensionless groups. We're going to make this dimensionless. We're going to write PR equals P by PC, TR equals T by TC, and that's all I need here. And ZR, if you want, okay, equals Z by ZC. Yes. So Z reduced. ZC is simply going to be VC PC by RTC. That's all. Okay? So I have a ZC. Okay. Let's substitute that inside here. Okay? That P dimensions and that P dimensions will cancel. Okay? The dimensions will cancel. I'm not saying the P will cancel. Okay? One of the T's here, dimensions will cancel one of the T's there. So you're going to get out of this minus 0 R of P. Well, we'll have to be careful. Something 0 to P R1. Okay? R times, I'm going to get out of this. Let me make sure I got this right. TR squared TC by PR ZC times DZR DTR PR DPR. Okay? Let's see if I got that right. I've got the negative sign, I've got the R there. This is PR, PR, TR, TR, TR squared. One of those, that's right. Okay, so this now, I can take RTC outside, and I'll get minus RTC times 0 to PR1 of TR squared by PR DZCR. Now, the nice thing about this if you can think about anything nice to say about it, is that the right-hand side, a lot of it can be written in terms of variables which are completely scaled. So I can write this as this. H minus HIG divided by TC is always equal to negative R times a quantity that is completely dimensionless. Completely dimensionless. And it's TR squared, PR, P reduced, DCR, TR, at constant pressure. R is the universal gas constant. So this means that if you give me a fluid, give me mostly, let's say, any hydrocarbon that you want. And as long as and let's say that I want to calculate, ultimately, the differences between these enthalpies. I'll need it when I'm going to calculate compressor in turbines and a lot of other stuff. I'm going to need something like this. I need this quantity itself, okay? Because you may recall that last time we went, we met, we had two states and a PT diagram, and we were trying to calculate enthalpy differences between here and here, and we went from H here to H there, H here to H there. This H and that H is my left-hand side, H minus HIG or something like that, right? So if I need this difference, I need my left-hand side, but I can go to a Mollier diagram, but that can be difficult. I mean, I have one, and then I won't have to do this. I can go to your Pure Fluids or whatever it is program you have. That may not be available. I can use an equation of state, but integration might be a pain. I can go to a diagram, almost, I don't want to call it universal, but an almost universal diagram in which I am going to be plotting this left-hand side versus this. This doesn't care what the fluid is. I don't see anything here to do with methane or octane or anything. This is purely in terms of an integral that has been computed once and for all. Somebody did it. Somebody went and took an equation of state. They already did it. You don't have a computer in front of you. They have already taken the equation of state. They have computed this universally because it can be calculated no matter what. You don't need to know the actual temperature and the actual pressure because this doesn't care what the temperatures and the pressures are. This is computed permanently. And that's what we'll deal with. We will then look at that diagram and say, from that diagram, if I know my input temperature and the input pressure, and I know the critical temperature and the critical pressure, those are usually easily available. I know T by Tc, which is TR, my input. I know P by Pc equal to PR. Another input, I go to the chart, locate TR and PR. It's true whether it's methane or octane or anything else. I don't need a new Mollier diagram for each one of those. It's once and for all. I plug it, I just go into the chart and read off this number. That's all I'm doing. Read it off. This is called the principle of corresponding states. Okay? And there's a diagram. So I will ask you to look at that diagram. I'll tell you in Canvas where to go. It's in the book. It's very easy to use. All you need is to look in the book and read out the critical data, plug it in, and you'll get the number. Okay? It's so simple. And that's what a lot of line engineers will use. You're out there working for PepsiCo or whatever it is, okay, that you're going to do in the summer, or Chevron or wherever you're going. You can do that. You don't need a computer, okay? You probably won't be given one anyhow. They probably won't let you, probably firewall you, okay? And won't let you use one. So you may as well go take your thermal book. Don't toss it away. Okay? Okay, we're ready to give out the exams. Okay.